process. If I not go for cleaning process, the identification and correction of those erroneous data, if it is not done, then ultimately it negatively impact the predictive model. So that's why there is a good proverb which is called, all good data are alike. They are similar, but bad data is bad data in its own way. So we have to treat individual bad data separately, and we have to treat them separate way so that the data can be a good data and which we can use as a fuel for the learning system. So that's why the machine learning system always is a data hungriness is there. It very much depends upon and sensitive to all those data which we are using, but we should not provide the data as a garbage so that it negatively impacted the predicted model. So data cleaning process is the initial part so that the bad data can be converted into a good data. Okay. Now the second question is how much data we need as a fuel, how much data we need. Do we have our own heuristic methods which actually decide that this much of data is good for machine learning? The answer is there is no as such own heuristic mechanism. Good data means if you have a bigger data, the result will be better. It is very generic way. So the bigger good data or the clean data you will be able to provide, you will get more and more better result. So that's why collection of data and collection of good data is very important for machine learning. So there is no as such hard and fast rule that this much data I need for this training, or there is no as such own heuristic method which actually decide that this much of data you need for this. But clean data as much as possible we need to provide the learning module. Now, what deep learning actually is? Deep learning is basically a memorization technique. So once we try to come up with some training data, it always try to give a model of interpolation. Now, what the absence part? The main absence part is the relationship in between the underlying variables. There is no as such relation in between those variables. And that's why the decision-making process, it can't be scaled up. And always this absence makes a huge difference. So always any neural network-based system, whatever the deep learning or whatever, they have very limited capacity to deal with the variations. So to overcome these things, what we need to do, we have to provide more and more variable data. As the data will be more and more variant, the variant will be, more and more variable data, which will actually covers all possible aspects of variation. The actual framework will work more and more better way. And in DNN, in deep neural network, always we try to generalize the things with out of distribution data inputs, and which is very common in this world. So that's why we always search for more variant data, because as much as variant data you will able to provide, that gap that it doesn't understand the underlying the relationship in between those variables, that can be neutralized. So decision-making process of this entire technique or technology, you can say, this underlying this variable relationship is the biggest challenge. This absence is the biggest challenge. So actually, once we talk about deep learning, we are far away from the integration of abstract knowledge. We not that much bothered about what the objects are, or what they are for, or how they are typically used. We only focus about like a bag, is a kind of black box. It's giving some output and we are happy with that result. But we are long away from this integration of abstract knowledge. Why? Why these objects? Why it is giving better results? And how should I typically use these things? So deep learning is not that much bothered about this thing. A 7-month infant, if you look into a 7-month infant, you will always realize that they always try to learn the abstract knowledge like rules. They try to find the patterns. From a small set of unlabeled examples, within a few minutes, they come up with some decisions. So that abstract knowledge like rules can be framed by a 7-month infant. But deep learning, there's a lack of mechanism of learning abstraction. So that's why we need sometimes millions of data, sometimes billions of data, or more than that. So there are two questions comes into our mind. One question is the robust deep learning algorithm, how robust the algorithms are. See, we are talking about in last 10 years, there are say 30 deep learning frameworks comes into the picture. But ultimately, we have to think in this way, that how robust the deep learning algorithms are. And the second question is, how much data is enough for quality training? So these two questions are the biggest question. One is how robust the learning algorithms are. And the second thing is how much data, quality training data you need for the training purpose. We will try to search these two questions answer in our, this further part. Let's talk about a very generic way. Suppose there is a single dot, it's a point, and we are trying to fit a polynomial curve. Now, say maybe the degree of 1 or 2 or 3. And you will see if I increase more and more data points, the generalization will be much, much more better. So which actually indicates that we need more data for better generalization. So as the data size increases, the generalization will be better. The polyfitting will be better. The order might be, it will actually cover all those points, data points we'll try. Or just think about the linear regression. The number of data points, if you try to increase, if the number of data points increases, automatically the point estimation will be improved. So that's actually tells you that number of data points is important. And the number of data points means the input, data input is important for any kind of generalization framework. Generalized, why do we try to generalize? Like say for KNN, if we try to give more number of data, we'll see the predicted class, the change in the predicted class in KNN, the data size is very much dependent. In fact, for the decision tree, the splitting actually depends upon the number of the volume of the data you are using for this. So all these things, these models or the generalized framework, you can see the number of data, it's very much actually, all these depends upon the number of data, how much number of data you are giving as an input. So better generalization requires more number of data. Now, what's wrong with small data? If I don't have large data, people talk about big data, but there are many cases where we don't have that much of data. In fact, in medical science, you will see most of the cases we don't have, there is a crunch of data. We don't have large amount of data. So once we have a small number of data, the basic problem is it's always mainly revolve around the high variance. The variance will be very high. The first challenge is overfitting. I will talk about more on overfitting, but it becomes very harder to avoid. We generally get some results, say 100%. It can't go beyond 100%, but it looks like that it is something, it's flooded and the result is giving 100%. So we don't only overfit our training data, but sometimes we overfit our validation set also. So these two things are important. Second thing is the outliers. So if the number of data, say 50, and the number of data is 50 lakhs, if there are 4 outliers in 50 data, and if there are 4 outliers in 50 lakhs data, you can imagine how dangerous it is if there are 4 outliers in 50 data. But the outliers is very common because we deals with data and there is noise. So noise has become very a kind of real issue in any kind of framework. So noise comes into the picture, and once the data size is small, it's something dangerous for the entire training model. Because once we go for training, we are actually trained with the outliers. So overfitting outliers, which is basically for the noise, for the purpose of noise, and the revolve around the high variance. These are typical problem of dealing with small data size, data volume. So we always, that's why fond of more data, so-called big data. Now, think from a different way. Starting in 2009, Professor Lee from Stanford University, they coming up with a large data set, which is called ImageNet, where 15 million data are there, hand annotated. So all 14 million data set with 80,000 distinct category or the class level. 80,000 different distinct category. And that the era of shallow machine learning. I'm talking about 2009. So 2010, 2011, up to 2011 was entirely shallow machine learning, that period. And the error rate was initially 28% recognition error rate. And then it dipped to 2%. The next year, there is a challenge. And this challenge, every year, this ImageNet challenge, the result improve and improve. There is a sudden dip in 2012 once AlexNet comes into the picture, 8 layers. Then each and every year, the new framework comes into the picture, and as well as the error rate getting lesser and lesser. Then after 2015, once the ResNet introduced, the error rate was getting lesser than the human error. It is becoming 3.6%. So it's a kind of paradigm shift in 2011 to 12. And there is a dramatic change in the entire vision computing. Because from 2009, we started from 28% error with 14 million hand annotated data and 80,000 distinct categories. And ultimately, now we are less than 2%. But how much data, parameters we need to tune? In 2012, Professor Hilton and their group, they come up with a nice paper. They presented that if there are only 1,000 categories, not 80,000, forget about 80,000. Only think about 1,000 categories are there. How many numbers of parameters you need to tune? 60 million parameters you need to tune. And 6.5 lakhs of nodes are there just to separate those or to classify those 1,000 categories. Now imagine if the count is 80,000, how many numbers of parameters you need to tune and how many numbers of intermediate nodes are there. So it's a huge number. So that's why this was one of the biggest challenge in this present vision recognition. So every year people are, the error is getting lesser, and now, it's almost touch 100%. So lesser than the human error. You can imagine that human can make error, but your deep learning framework will not make error. So we are in a good position. We are in vision computing. We think that, okay, now we are in a position that human can make error, but the machine can't. What is the reality? Is it the reality? Now think about it. Actually, once we talk about all these things, we have to think in other way also. That in computer vision, the key challenge is we deal with the variance of data in real world. Now, real world data means the objects are taken from different angles, different backgrounds, under different lighting conditions. Their illumination is different, their brightness is different, contrast level is different. So they're captured, and that background is also maybe changing and maybe dark background, and they are captured in different angles. So it might happen the objects are partially occluded, or other object maybe the colored in the way. Maybe you can think about it. There is a shadow which covers a major part of the image. Our vision system, our human vision system, from those clues, they can come up with the entire design. The pieces of the knowledge can fill those missing information. We can reconstruct the image. But deep learning fails to do this. Means creating AI, actually, we are trying to reproduce that object once we try to recognize that object. But that partial occlusion, that shadowing effect, which is very common in our vision system, we can, looking at very small part of anything, we can entirely redesign, or say from that clue, we can think that, okay, this is this. But actually, it not happens. So that's why CNN is designed to cope with translations. That means a well-trained cognitive are talking about that object, regardless where it is appeared in the image, it can catch. CNN can catch. The object can be anywhere in the image, it can catch. But it is not good if the images are the changing viewpoint. Means if it is rotated, if it is scaled, CNN sometimes not works fine. Or most of the time it not works fine. That's why Professor Hilton, giving this statement that CNN's design is scope to translations only, full stop. And after the next part is changing viewpoints such as the rotation, scaling, etc., which is very common, where deep learning, rather better to say the CNN frameworks not perfectly work. So we need to gather massive amount of image that actually display each object in various positions. Maybe from 360 degree, we'll try to capture the images. All variants of the data we'll able to capture. We used to train our module with a large volume. That's why CNN is, say, hungry about data. The object needs to be generalized, and it may be, you are trying to map with the real world object. So it needs to be from all side, all direction, all viewpoints image captured. Now think about that ImageNet. ImageNet contains 14 million annotated data, hand annotated data. It's not a matter of joke. But all those 14 million data by which we can actually benchmark our result, which is actually for use for the evaluation purpose of any vision computer standard system, it proven to be flawed. There is a flaws. What is the flaws? The flaws is it's a big data size, a huge data, 14 million data, but it fails to capture all possible angles and the positions of the object. It mostly composed of the image that has been taken under an ideal lighting condition from a good known angle. So always we try to capture from some point where we'll able to get that whole image, and we will try to get the image in a correct way, in a proper lighting condition. And they did the same thing. These 14 million data, they are very high quality data. They are actually taken in ideal lighting conditions. But in reality, it's not like that. If you look into this ImageNet, chairs looks like this. But think about in your room. Actually, I don't know about your room, but my room, it's a messy one. The chairs are rotated, the chairs are flipped, the chairs are, backgrounds are there, the viewpoints are different. The teapots, you can imagine, these are also teapots. These are also t-shirts. So ImageNet, the t-shirts looks different. But here the t-shirts are completely different. How CNN can work? Our vision system can recognize, okay, this is a t-shirt. But the lacking part is we don't know the abstract knowledge. That's why we will not be able to capture, we will not be able to relate that this is a t-shirt. And that is the major issue of CNN. Think about this particular picture. Do you think that CNN will be able to understand that this photo and this picture is same? No. A vision computing, I mean, if you try to think that from your perspective, your vision system, it's easily identifiable. Anyone can understand, okay, it was captured from, say, aerial photography or maybe states, whatever, Washington, DC, etc. But for CNN, think about it. How they've taken from different angles. If you only trained with different angles, so all shots of angles, 360 maybe, then might be your CNN will give you a better result. Otherwise, it does not have that capability. Okay, so the acceptance of human vision system, which can easily generalize its knowledge, creating object from a few angles. Usually that image what you would like to, I mean from a new position if you are giving, or under a different lighting condition you are giving to the system, it failed. So CNN, actually it do not have any creative mind like human being. So how can you solve this issue? How can CNN deals with these things? There is no creativity like a human being. So that's why we need something called data augmentation. So data augmentation is some kind of solution, which I will talk about more on this data augmentation. But this is one particular solution maybe. But ultimately, fundamentally, Professor Hilton in a particular conference in AAAI, in the Artificial Intelligence Conference, it's a top tier conference. He said that CNNs are fundamentally flawed. Why? Why he said this? There are many reasons. I can tell you one reason. Professor Hilton said that the pooling layer is the biggest mistake. What the big mistake is, because you are losing the valuable information that you are ignoring. Actually, maybe there is a relationship in between those parts or as a whole, but you are ignoring that relationship. The underlying relationship you are ignoring. You are trying to pull max, you are trying to pull average, but you are losing the valuable information. Think in this way. There is a face. There is a mouth, two eye, face, oval, nose. Face, oval, and nose are there, and you draw a separate figure, but these same 5 prominent features are there. Highly probable features are there. And they will be catch that they are same. CNN will tell you they are similar because all 5 features are there. They are in place. But do you think that this is a face, the right side one? Vision computing will tell you that human vision will tell you, no, this is not a face. But CNN will capture those 5 features and it will return that, okay, these are similar, which is not good. So this is one flaw. There are multiple flaws are there, but I'm talking about one. So these are the challenges. So that's why, as we started 14 million data set, so we need millions of parameters. We need fast hardware. We need lots and lots of data. The model size increases, the data size increases, the complexity of the problem domain increases, and it's logarithmically. Think about it. So the answer is yes, it's okay to invest time and money to gather more data. It should not go for small data. Rather, it is always good to go with large data. Collect your data, invest time and money for this, gather the data, go for cleaning process, come up with good data, all sorts of variations, so that those challenges can be overcome. So that's why it's a good saying that yes, it's okay to invest time and money into gathering more data. Okay, so am I audible until now? Or
Yes, you are.
Yes,
okay.
sir. Yes.
Thank you very much. Okay, so what's wrong in medical data? So medical data, the biggest problem is doctors try to annotate or hand annotation, manual annotation, which is very time consuming. They are busy. These fellows, their fraternity is entirely busy with new things, their new patients. So they don't have time. So clinical expert typically provide always a small size data. And the second challenge is all different countries, they have their patient privacy laws. Like European Union, or all countries, they have their own data privacy laws. And the major issue is the mental blockage. If I have some sort of chronic disease, I not want to share my chronic disease related information to other people, or in fact for the biomedical images also. So that's why there is always a crunch of healthcare data. And once we get, say, 100 CT images, 1000 CT images, or 1000 MRI images, we feel so lucky. Think about it. One particular framework you are deploying for 14 million data, and other side you are happy with 1000 data. There is some imbalance. So data is important, but gathering the data is very difficult. So the limitation is annotated data, which is a major problem of healthcare. So most of the cases we deal with very less variant of data, small size data, and that is one of the biggest challenge. Now, if you look into some standard data sets for segmentation, say organ segmentation, different modalities starting from CT, MRI, PET, or say Q1 MRI, etc. Maybe the abnormalities can be in the brain, breast, cardiac, maybe liver, lungs. All these data sets, look at the size of the data. 82 samples, 79 patients, 339. So only the biggest one is this one, 1250, I think. Oh, no, there is another one, 1397. So this number is good for deep learning. Do you think so? So how to deal with this data? How can I give more inputs? How can I give more variance data? So the answer is, as I already said, data augmentation. And we know these things. The data augmentation is a kind of, say, image manipulation technique, where basically we go for geometric transformation. We have a common base image. From that, we go for translation, we go for rotation, we go for flipping, we go for zooming, zoom out, maybe stretch, maybe shared. All these are geometric transformation. Not only this, maybe the elastic deformation. You change the variance level, the deformation will be high at a particular deformation level, you will stop. Or you go for contrast augmentation. Maybe you stretch the histogram, go for white balancing, sharpening. That's the color augmentation. In fact, there are some techniques like random cropping. You randomly crop a particular part of an image, and you create multiple images from the base image. Or maybe the mixing of image. Maybe there is a foreground and background. There is a blending, which is called the alpha blending. There is an alpha channel, and you are giving an alpha value in between 0 to 1. And based on that, it decides that which will come foreground, which will go background. So if you can recall that era where we had some TV at our home, there was DD1 and DD2. So there was another channel which is called alpha channel, where we switch from one particular channel to another channel. So one channel will come to say foreground, one will go to the background. It's a kind of blending. So in this way, we can create multiple images. Or maybe the kernel filtering, where it's a Gaussian kernel, we change the variance and we can create multiple images from one particular image. But there is also another problem. The problem is, suppose this is a CT image or this is a, say, X-ray image. You are creating 10 images or 20 images from some kernel filtering technique or say random erasing technique. But think about it. All those images are actually generating from a base image because their parent image is same. So somehow all those images are biased. So you are actually giving input to your training system where the data are redundant data, biased data. There is what, I mean, think about the advantage. Do you think that it properly works because we are giving biased data to the system? It's a kind of similar kind of thing. You have an X-ray, you partition the X-ray into 5 pieces or say 6 pieces. And you said, okay, I have 6 X-ray. It's a kind of, can you give me a say change of 100 rupees? You can say, I can't give you 100 rupees change, but I can split it into 10 different parts. So it's a similar thing. So you can't split it. You can't split the X-ray into 5 parts or 6 parts or 8 parts just to increase the number of data. Think about it. Data augmentation technique, image manipulation technique, which is one of the widely used technique just to increase the data for the deep learning framework. All data are somehow biased. Okay. So people start thinking about, to solve this issue, we should go for using some deep learning approach. To solve the issue of this crunch of data augmentation, they started thinking about GAN. So when GAN comes into the picture, the cycle GAN, you can change the autumn scenario into winter, winter to summer, summer to autumn in this way. But it's very robust system, computationally intensive system. And actually we are fond of alternate solution, cheaper solution. So what is the cheaper alternate? So before going to GAN, we should go for the cheaper solution first. The cheaper solution is neural trial transfer, where we actually try to change or grab the texture, ambience, appearance, background of a particular image, rather better to say of the style. That style we want to inject to another image. And in this way, we only change the texture, continue changing the texture. And one particular image can generate more number of image by tile transfer, just like this. Suppose if you have, say, one particular style, from that style, maybe it's a study one, from there you change the style and you can create from based on the song, you create another image. You change the music, you change the theme of that image and you change it to another. So same image can be translated or transferred based on the framework, neural trial transfer. But this cheaper solution, where, I mean, actually we'll see in many of the medical cases, like say for MRI, like a great way for Kanagwa, this after a certain number of iteration, 4 or 5 iteration, behind this MRI, there is a neural trial transfer. And these are the prominent neural trial transfer. So one particular image, you can create multiple images only by changing the texture, changing the appearance, changing the background. So it's a kind of neural trial transfer. And another solution is, which is a very common solution, which is called the GAN. So if you have a true contrast CT images, from there you can create synthetic images. So synthetic images looks almost similar. There's a kind of the abnormality presence in the real one. Maybe here also you will find some abnormality, and it actually works. It created by GAN, and it actually works. And many of the cases we increase the data size by imposing this GAN. So something a little bit about GAN, because GAN is a kind of, you can say it's a synthetic data generator. So there are 2 modules. One is called the generator, one is called the discriminator. Generator, what try to do? It always try to create the fake data, and it pass to the discriminator. So maybe the fake rows, fake maybe any kind of music, maybe fake faces, and it passes to the discriminator. And what is the task of the discriminator? Discriminator always try to predict, or rather better to say that based on a particular probability, they try to separate that, okay, this is a particular image which is fake image, this is a real image. So think from here, there is a noise pool, latent space. From that noise is a Z, which is maybe the normal noise or uniform distribution noise, which is passes through the generator, and that noise is generating some fake images. And there is a real sample pool that is also passing to the discriminator. And discriminator task is just to discriminate that the image coming from the generator is a fake image and that coming from the data pool is a real image. So it tried to discriminate, this is real, this is fake, this is real, this is fake. So discriminator is basically a classifier, whereas generator is just to create or generate the images. Generator always try to make the discriminator full, but the discriminator always try to pretend that I am not getting fooled, and it stop where it get fooled. So somehow there is a tussle in between generator and the discriminator. Now what happened? So the input is Z, the noise. It passes to G. There is a theta1 or theta2, maybe the parameters which you need to tune, and it creates an image which is a fake image which is called X. X is passes to the discriminator, and that dx theta2 give, I mean, it always try to classify, discriminate that it is fake or it is real in between the probability value that is a 1, 0. So it's a classifier or the discriminator based on some probability. It will tell the fakeness of that data. Now what happened? So the training, it always try to, there is a two part. One is maximizing part, one is minimizing part. What it try to maximize? The real data should go to the real data pool, and the fake data should not go to the real data pool. The fake rows should not go to the real rows pool. So we need to minimize one part. And the real data, real rows, it should go to the real rows part. That is the maximization part. So there is a max-min issue, max-min problem. But think about it, once there is a classifier, there is always a loss function. There is always an error function. So in between this max-min, once it tried to classify, there is some error, there is some loss. What happened? Generator always try to make fool the discriminator, and discriminator try to save it from getting fooled. But in between this classification, one particular error function or loss function comes into the picture, which maximize the D of ZZ. The discriminator and the part is the G of Z. Now, what happened? If the probability, if say suppose if you are using the loss function, if the penalty of the loss function is high, that means you are doing some error, you are making some error, and you have to give a high penalty. What will happen? It will try to do less error. That is our tendency. So machine learning having a tendency, if it is logarithmic, then automatically the penalty which needs to be given will be more higher, and the chances of doing this error or a loss function, it will be lesser. So it incorrectly classification tendency will be getting lesser. So that's why we use log loss. Now, once you use this log loss, after several steps of training, one point will reach that the generator will not be able to create more and more synthetic data. And the discriminator will unable to fail that the data which is sent from the generator is a synthetic data. So that is the convergence. So always try to optimize the oppose loss function. Somehow the oppose loss function, it needs to be minimized. That max-min game theory plays an important role for this, Professor Nash equations. And that equation actually is a max-min part which actually optimizes that the loss function, it controls the loss function, one-time convergence reaches, and that part, the generator failed to create more synthetic data, discriminator failed to catch that it is a synthetic data, it is getting fooled, and ultimately, it's a win case for the generator, the synthetic data generates. So I think many of you already know about GAN, and so you have GAN about this GAN. So next is the transfer learning. So transfer learning is, once the data size is very less, how can I solve my problem? So you have different tasks to solve, you have different learning system, you acquire knowledge from different learning system. Those learning, whatever you learn, you will try to pass to solve a different challenge. That is the main thing of transfer learning. So what we do, suppose we have an ImageNet, and what we are trying to solve, the size is very, very less. So the data pool is very less. Say, for example, in 2020, in February, once we first come up with a prediction model of COVID, that is maybe the very first paper on prediction model. So that time, there is a main issue was the crunch of data. We don't have data that time. So how will you solve this thing? So you have a large set of public data set. So from there you extract the feature, go for classification on all, solve that problem, deep learning framework, pass that knowledge as a pre-trained knowledge or frozen knowledge to solve a task called B. And that task where the data size is very less. So what you need to solve a particular problem, what you are trying to do, you are solving a different problem. You are gathering the knowledge, and that acquired knowledge you are passing as a frozen knowledge or pre-trained model, better to say, which pass to the transfer learning module. Interesting part is it requires fewer number of parameters, much more faster, and it's computational. The resources which you need for other framework, it's not that much because you are separate way you are dealing with that data. So that's why transfer learning is very, very, you can crazy thing for medical imaging. People use, many people use transfer learning to solve this kind of small data problem. But the data which you're using for solving this means from the solving B problem A to solve a problem B. For solving A, do we use similar type of data or we will use different domain data? So suppose for say one histological image we are dealing with. So am I need all histological data for this transfer learning model, or I can take knowledge from a database like ImageNet where there is cat, dog, rat, mat, etc. So these are the same data, domain data or different domain data. So for interesting part is, if you go for training module, you load the pre-trained module first, whatever that, maybe the last layer. The first layer, you are trying to capture the low level features like color, edges, etc. And the last level feature where we are trying to find out the more specific features. Those more specific feature can be replaced maybe by best cancer classes, those features, so that the model will be more tuned. The training mechanism will be more tuned. Ultimately, the accuracy may be based on the voting, majority voting, it will give you a good result. So what we're trying to do, we can use any database, but maybe that needs some training at the end level. So in the first layer, we are not going for this. We are trying to capture only the low level features, but at the very end, there are very high level features, which is very specific to that particular disease or the organ or the modality, better to say. So those things can be replaced with a lesser size of data. So that 4 classes, that is called the 4 classes. So those 4 classes can be injected to the system to make the training module more robust. Ultimately, it will give you better results. So maybe it will say you that it is in situ or say benign or malignancy is there, or maybe the normal cases, histological data. So another thing is called the one-shot learning. So I don't need data. I have lots of data. I have only one data. I have few data. Think about it. I don't have any data. The model can't look at the data example in the target class during the training. It is called zero-shot learning. And it is reality. And one particular company, I'm not taking the name, they are working on this for face recognition system for a long period. One-shot learning. You observe the model, observe the example for one time, model observe. Then the training complete. And the second last one is a K-shot. K number of samples or examples are there. Based on that, you are trying to do. Think about it in this way, that you never saw a person from movie who is an actor, but you can recognize. If you saw him in the market, you can recognize this guy is that particular guy. So based on the K number of learning. So this is typically, as I said, is used for the face recognition module. So Siemens comes into the picture where this that NVIDIA wants to come with the scan generated faces. These faces, once one-shot learning deployed, it is seen that two pictures contain the same dog or the same cat, it failed to identify. If a person having, say, wearing, say, hat or scarf, maybe the glasses, the person is other from the other images. It's not exactly they are same. So what about the accuracy? That was the question. But still, in 2015, there was one interesting paper published in Medical Science where one-shot learning deployed is unfolded in the brain. So it's a kind of one-shot learning is an on-off kind of thing. This is a very interesting paper. You can go through this laws. And this paper tells you that people actually, after this, if you see, almost it's 6-7 years down the line, there is no as such good work comes where one-shot learning or this type of learning can deployed. I mean, it's not like a kind of groundbreaking kind of thing. Still, there is a scope of work. Now, these are all some challenges and issues. Now, the second part, the rest of the part, I will more talk about the solutions. So what are the solutions? How can you deal with all these things? So just 2 to 3 minutes break. Okay, thank you. Until now, it was clearly audible. Can you please write this?
Yes, sir, it was audible.
Yes, sir, it was audible. Okay, okay, thank you. So one thing is which is called the patchwise training. So patchwise training is just to avoid the redundancies of full image training. Like suppose, for example, that once we go for semantic segmentation, we always try to classify individual pixels. Okay, not by the whole. I mean, so we don't need actually the whole image. So adding lots of redundant parts in the input It's not required actually. So it's redundant informations we are trying to put. So that's why patchwise training is very important, which I mean, ultimately it improves the complexity. So batches of random patches we need to feed to the system just to avoid during training process the network congestion. It's a kind of not, I'll typically not say this is congestion, rather better to say the standard approach to avoid this kind of problem that we are putting more redundant data. So rather it is better we will go for patchwise training. This is the first thing. So patchwise training is a kind of patchwise sampling. We are ensuring that the input has enough variance. So the valid representation of the training data. And once you give more prominent data, more patchwise after sampling, you give the good data. So not the redundant data, the convergence will be faster. And it will actually try to balance the classes. But the problem is once there is an overlapping patches, you will get ultimately higher accuracy because you are feeding same data multiple times. But it is computationally intensive. It's very simple because same area, same particular pixel, if you are trained for multiple times, that means it is getting overtrained. So it will give you higher accuracy. The intensity, I mean, the computational point of view, it is the intensity, it will increase. It will be intensive. But ultimately, the result will not go. So overlapping patches is a big factor, which is directly related with the performance. And always we have to think about the size of the patches. It should be many patches. It should not be a large patch. So these two things need to be taken care once we go for patchwise learning, training. There is few interesting work, like here you can say people are trying to extract, the researcher are trying to extract the patches. Then they go for augmentation. So it's a kind of patch extraction. Then after that, patch-based classification, then labeling. Here, like say there is a normalized histogram, say histological images. That histological images passes through the patch-based extraction based on the texture, maybe based on the color feature, maybe any kind of such kind of feature, contour, etc. So ultimately, those patches goes to the training module. There is a transfer learning module, PGG19, then go for the layer fusion. There is a fine tuning. Then after that, ultimately, there is a majority voting and it gives you some predicted result. So the interesting part is you are not trained with the full image. Rather, you are going for patch-based training once you go for semantic segmentation. So it's a kind of patch-wise training, which resolve the issue, which actually increase the performance. The convergence will be faster. That is the important thing. Okay. Another thing is the weak supervised learning. So supervised learning and weak supervised learning. Weak supervised learning is very interesting thing. So it's a kind of always, it's very difficult to come up with hand level data set because it's costly. We already discussed. And in reality, it's always not possible. So weak supervision, which once we go for weak supervision, what is the thing? The thing is you have noisy data, limited data, imprecise source of data. And you try to supervise signals. You try to level the large amount of training data. So based on that, you increase the volume. So because as it is expensive, so from that supervision, you are trying to level to data and you increase the volume. So it's a kind of weakly supervised learning. Now, if you think the unstructured data framework, so majority of the data in real life is unstructured. So high quality annotation, which is actually given by the domain expert, there are two parts. One is the large annotated data volume. We'll go for supervised learning. And if the small annotated data size, which is basically the semi-supervised learning or the transfer learning. So if it is semi-supervised learning, it's a kind of less accurate. If it is supervised learning, it's too expensive. Otherwise, the transfer learning may be more accurate. Or another thing can be done, that is the unstructured data can be and non-annotated data, which is unsupervised learning framework, where there is non-overlapping classes may be useful for this purpose. So a little bit insight about this middle in between these two, no annotation and high quality annotation. So suppose think about low quality annotation. Low quality annotation means you don't have no annotation case, you don't have high annotation case like supervised, semi-supervised, transfer learning kind of cases. So what we try to do, we will try to, cheap annotate from the non-expert. And somehow from the non-expert, we'll try to get some annotation. Then we will try to deploy some heuristic strategy to identify the patterns. Then from that batch of annotation, we'll try to form some data. Using the noise, we'll try to predict the pretend model. So it's not taken from the actual expert. Rather, it's a kind of noisy data which is taken from the non-expert, which is a cheaper solution. From that, we try to find out some heuristic strategy to find out the pattern. Then we try to make it cluster. Using that noisy prediction result, we try to put into the training module, which ultimately maybe improves the overall supervised learning module result. So once we have a crunch of this kind of high quality annotation, and we need some sort of annotation, once, what is the solution? The experts are busy. So non-expert need to give the solution. It's a cheaper solution. You take any cheaper solution from any non-expert, you identify the pattern, you try to form the cluster. From that cluster, you try to predict. That prediction result can be passed, or the leveling can be passed to the supervised learning module. So this is basically the weak supervised learning. I think the idea is now clear. It's a kind of, you can say, the high quality data set, to overcome these challenges. If you have a limited high quality data, the domain expert maybe later can sample. So if you initially they don't have time, but later once you come up with this, the outcome can be rectified by some domain expert. That can be a further one level ahead tuning. So semi-supervised learning, supervised learning, weakly supervised learning, transfer learning, it deployed in all different modalities, different disease, different architecture. So you can see there are, say, AB is used for 1 and 3 classification model, or say segmentation models, regression model for supervision. In fact, for the weekly supervision model, the supervised model deals with the multiple instances learning model. So it's a kind of MIL module, etc., etc. Now the second thing is the third thing is the sparse annotation. So what is sparse annotation? Sparse annotation means the fully annotating data is not always possible. We already discussed. And for 3D cases, it's almost very difficult to get fully annotated data. So we need some sparsely annotated data. Sparsely annotated data means, you can think in this way, there is a switch. So the weights are unlabeled data are set to 0, and the weights are labeled data set some value. So only learn from the label pixel if there is some value. So that is called the sparse annotated value. So you can imagine there is a sparse matrix, 1, 0 matrix, number of, say, non-zero element is more than the 0 element, similar kind of concept. So here there is a 1, 0. So you give weight if it is labeled. If it is unlabeled data, that particular pixel will be set as 0. So you try to separate out that this data is not contributing, this particular pixel is contributing. So it's a kind of filtering. It's a sparse annotation. Automatically, it improves. Now the question comes into our mind that suppose I have very, very good quality data. All data are true positive data. We don't have any negative data. False positive cases are not there. So you are very lucky that you have all data, good data, all positive data, all true positive data. Classifier works not good. Why? Because classifier is not able to discriminate the false positive cases from the true positive cases, because there is a crunch of false positive cases. So to enhance the discrimination power of any kind of network, we need equally false positive cases. That negative set of data which actually needs to be injected so that the discrimination power of the network will increase. This is called set, which is efficient negative set or effective negative set. So it's a kind of, you are trying to increase the discrimination power of the classifier by increasing the false positive cases. Think about it. Suppose there is a disease which is not there in North India, but there in South India. So if you try to classify, how can you classify? Because you don't have any false positive cases. You have only positive cases, or you have only false positive cases, no negative positive cases, true positive cases. So there needs to be balanced. So negative data is important for the classifier to discriminate, for the network to discriminate. This is another thing. We always need to keep in mind, what is the distribution? What is the distribution of false positive cases and negative cases, or the negative data and the positive data? If the polarity is good, discrimination is good, networking ability to discriminate will be also good. Come to the another one. That is called class imbalance problem. So class imbalance problem means a very small part of an image is actually we need for medical image processing, which is called region of interest. I think you already encountered this terminology. My friend Vikrant or maybe Donde sir or Ram sir told about these things. So these small portion of an image, a very small portion of an image, that is very interesting thing. That is called the region of interest. Remaining part, I don't care. I don't care about the background area. I don't care about what is written, the textual, I mean the patient detail or whatever. Now, I am only interested about that lesion. I'm only interested about that part, which is say containing, say, maybe malignancy. So small organs abnormality is greater, having the greater importance. So that's why what we need, we have to train our system with a small patch. So again, the patch selection comes into the picture, the patchwise training comes into the picture. But it needs to, if you give more and more background, the classifier will be biased and it will get trapped into the local minima. So you should not give those redundant information, unnecessary information, background information. So that's why the reweighting, sample reweighting is important. Which sample needs to be in the foreground? Which sample needs to be in the background? Which is my non-region of interest, which I don't actually require. So that's why the solution is the path-based training. But the problem is the class imbalancing. Okay. Now come to the another challenges with the training of deep learning models. One interesting thing is in medical imaging, people used to get always, I mean, they are looking to some result like 99.9% accuracy, sometimes 100% accuracy. Always think from other point of view. Is this a case of overfitting? Because once you train with some data, maybe some positive data or less data, you will get some result, which is very good. But ultimately, it will not work for new data, unseen data. The model is not generalized. So model learning pattern specific to the learning data, which is irrelevant to other data. So that's why the important thing, once you identify, okay, I think something is problematic in this case, why this accuracy is too high, look into the validation matrix. Look into the training matrix also. If you look into the training matrix, you will see the result is improving because the model seeks to find out the best fit in the training model data. So it continues to improve. It continuously improving. But the validation matrix, if you look into this, you will see it stop improving after certain number of epoch. So after certain iteration, you will see it's gradually decreasing. That actually indicates, the validation matrix indicates, okay, initially it was improving, but now it is decreasing. That means there is an overfitting case. So to identify the overfitting case is very important. Once somebody tells that I got 100% accuracy, 99% accuracy, in medical imaging, we used to say, what is the sensitivity? What is the specificity? How much it is efficient to identify the false positive cases? Because if somebody don't have disease and your machine CAD system is saying you are having disease, then ultimately it's a psychological pressure. So that's why we always crazy about those numbers, PPV, NPV, ROC curve, AUC, etc. And you always try to look into these two matrices. Result is good, show me the validation matrix. If the validation matrix is continuously increasing, I am done with it. But if it is decreasing after a certain number of epochs, that means there is something problematic. It's an overfitting case. Okay, so what is the solution? Solution is simple solution. Increase the data. If you have less data, it will overfit. If you increase more data, it will not increase. But unfortunately, in real world situation, medical data, there is a crunch of data, budget issue, technical constraint. So all these things are there. So ultimate solution is something different. Think in this way. You have to lower the capacity of the model to memorize the training data. Now you are saying, I don't have many data. So what I need to do, my training module will not be able to memorize more. The memorization of the training data will be lesser. So think about it. You are trying to control the memorization of a training module. Of the network, you are controlling the memorization. You are trying to lower down the capacity of the model's memorization so that the overfitting case will not occur. I think now the idea is clear. Why we try to minimize the memorization power. How can you do this? The one solution is reduce the network capacity. Remove the layer, remove the number of elements in the hidden layer. In the very first session, I saw one question in the chat box that how many numbers of hidden layer we required for any neural network framework. This will, at the later part, we will discuss about this. So we always try to reduce the network capacity. If you reduce the network capacity, what will ultimately happen? End of the day, the memorization power will be reduced. So you have less data, less memorization. That means overfitting chances will be lesser. Or you can go for regularization. What is regularization? Regularization means you are trying to give some cost to the loss function or the large weights for the large weights. Whoever the large weights, you are giving some loss function. That loss function can be given two ways: the absolute value of the parameter or the square value of the parameters. So if the result is sum of the weights to equal to 0, other way the result is smaller weight. So it's a kind of L1 regulation, L2 regulation. Or the last third option is the dropout layer. So you are randomly removing certain features from setting them to 0. Now again the question comes into our mind. If I drop out, if I go for pooling, I am losing information. I am losing the inherent connection in between those patterns. Am I a loser? Is it a false system? Yes, this is a false one. Because you are dropping out the layer without knowing that these are interrelated or not. The abstract knowledge we don't know. So that's why the reduction of networking capacity, regularization and dropout, these are the few solutions to cope up with the overfitting cases. Okay. So another way is the tuner, which is called the learning rate. The learning rate based in stochastic gradient descent. What happens? If you're trying to optimize the algorithm, you are trying to estimate the error gradient, the current state of the model, example, the training data set. We try to update the weights. So the weights are updated during the training process. By how? By the learning rate. So learning rate is kind of a step size, the step in between 0 to 1. So learning rate is comfortable. It's a kind of hyperparameter you are trying to tune. Now, if you ask me 1,000 classes, 60 million parameters, so maybe 80,000, maybe 6,000 parameters, hyperparameters, you need to tune. Can you tell me one parameter if I ask you to tune, if I give provision to tune one parameter, which parameter you will choose? I will choose learning rate. Because learning rate ultimately affects the whole network by changing the weight in a step. What is that? Suppose, think in this way. Suppose the learning rate is 0.1. That means the entire network, the estimated error into 0.1 or the 10% of the estimated error each time the weight is updated. So it's a kind of the error estimation of the entire amount of the error which is passing to the node. You are trying to slice down. You are trying to slice down by learning rate. You are not multiplying with the full amount, rather What you are doing, you are slicing down by learning rate in between 0 to 1 value. So in this way, you can control the learning rate, the step size, the weight can be tuned. So now the question is, which optimization technique is good? So the algorithm should tell you that, okay, I have an algorithm so that I can choose that this particular algorithm, this particular optimization technique is good for controlling the overall, the learning rate and all for this entire framework, stochastic gradient framework. There is no hard and fast thing, but still Adam is a good one, Ada Delta is a good one. So we generally use Adam, but apart from Adam, multiple can be used. So this is what the learning rate, which needs to be controlled, which is in our control. The step size and the weight can be, updation can be done by our end, only by tuning the learning factor. And I think this is one of the crucial things for deep learning, to set the learning rate so that the entire network will accordingly work. Now comes the gradient vanishing. What is vanishing? The gradient vanishing is a kind of often gets smaller. The gradient is getting smaller. Suppose think about a backpropagation neural network. The backpropagation neural network, the error is feeding to the front side from the output to the input, and the gradient in between this input and output is getting lesser, and approaches to 0. Eventually, it leaves the weights of the initial value, or the lower layer is nearly unchanged, the input and output. So gradient is not there, dy dx is not there. So how can it be descended? So gradient descent never converges to an optimal. That's why it is called the vanishing gradient problem. Think in the opposite side. If the gradient is increasing day by day, time by time, say the input and the output, the gradient is increasing. So getting larger and larger, this gradient, that actually also never give you convergence. It's called the exploding gradient problem. So one is a vanishing gradient, and side by side exploding problem is also there. But we more talk about vanishing gradient because we try to propagate the error, and it is the balancing getting 0, and there is not eventually any kind of weight differences with the initial value. There is almost unchanged, the layer getting unchanged. There is no gradient as such, and we say, okay, so there is some vanishing cases. But equally, parallelly, you can say side by side, these things also can happen. This can getting larger, the gradient, and ultimately it will also affect the entire network. Okay, so what is the solution? The solution is, once there is a gradient vanishing issue, the intermediate hidden layers output will be upscaled. Because the gradient is getting lesser, so I have to do in between the hidden layers so that the gradient will be higher. So if I convoluted the matrix, which is called the sum of product operation, we have to do deconvolution to scale up it. So it's a kind of reverse technique. So that it passed to the softmax, the prediction result will be good. So that's why there are a few other solutions also for, originally once you try to do these things, you may need to go for proper weight initialization. You maybe the activation function which you are used, that also sometimes makes a big issue, like if you're using a ReLU or etc. Maybe batch normalization, or sometimes there is another technique which is called gradient clipping. You need to clip the gradient. So particular gradient you need to clip so that ultimately it will increase the overall gradient. The vanishing will be not there. So these are some solutions. Now, another thing is, imaging is a kind of thing, medical imaging. The major challenge is the image which we actually use, it's very much depends upon organ, very much depends upon patient, very much depends upon patient, the demographics of the patient. It's all depends. The modality depends, everything. So that's why the shape, size, location from patient to patient, it's varying. There are different cases you will face. Like say the boundary might be it's ambiguous boundary. The contrast level, because of the contrast level, you are the targeting organ and the neighborhood tissue. You are not be separate out these two. So these type of challenges are there. multimodal approach, multimodality, if you're taking, say, supervised by something, one particular modality supervised by this. So that thing might be gives a solution. So it's a kind of, you are doing one particular modality, but parallelly you are helping, taking a support of another modality. Looking at some modality, you are doing another modality. It's something like this. But one solution is superpixel information. Superpixel information means, suppose you are representing one pixel into 2 cross 2 matrix, into 4 pixel. So the dimension of the image will getting higher, 4th time. So it's a kind of superpixel information. Just the segmentation overlapping or the organ boundary will be more prominent. Because if your dimension is, say, n into n, and if you change it into 4n into 4n by superpixel, every pixel is superpixeled, upscaled into 2 into 2 matrix. Ultimately, the size will increase, and you will see the non-overlapping cases will be more prominent, overlapping cases will be more prominent, and ultimately you'll be able to extract the boundary of the organ. So we are almost at the end. Then after that, if any question session, but few more slides left. So there is a news comes a few months back that highway, there was some tray, and in that tray there was 99 mobile phone, and it fooled the GPS system. So it was like a human created condition. Think in this way, that in 2019 in TEC, this particular paper published, where they shown, the author shown, that if you omit a single pixel from the image, single pixel, 1 pixel from the image, the aeroplane will be classified as dog, or the deer will be classified as dog, the frog will be classified as dog. So think, one pixel, only 1 pixel can make the entire system full. And there are multiple images they shown in this particular paper work, where they shown one particular pixel, if you omit or if you add that pixel, that makes a difference of discrimination, classification. That's why this Marcus said that deep learning systems are quite good in at some large fraction of a given domain, but yet easily fooled. Okay, so more work needs to be done in this area so that we can make the system more and more robust. Something about the medical ultrasound analysis, as I am mostly from medical imaging. So there are methodological tasks like detection, location, classification, segmentation, registration. So I think there is already one session on CAD system, computer-aided diagnosis. So those part may be completed. Then the clinical task part, that is the biometric measurement, that the physiological biometry, maybe the structural biometry, etc. CAD system, image-guided intervention, or the therapy. Or maybe it depends upon the organ, UV, that is the breast, liver, etc., heart, brain. If you look into this, and if you go through this particular paper, which is cited at the bottom footer, you will see the number of paper published in last, say, couple of years. Most of the paper published in the area of, in 16, 17 are on segmentation, detection, and classification. And majority of the work is carried out in the area of CNN and other neural network framework. So CNN are taking a leading role. And majority of the work has been carried out in heart, breast cancer, prostate, etc. So this is one, you can say it's a trained analysis, you can say. This particular paper actually reported this. I thought it will be interesting to showcase these things so that you understand that in which particular modality people are more working. So these are the area where you can work, like bone, carotid. Actually, the initial day, 10 years back, I used to work in carotid and coronary intravascular ultrasound images. But then after that, the lymphatic node, the muscular, the kidney is also there. There are few competitions on medical imaging. These are the top-notch competitions, not only the Kaggle ones, but these competitions, if you go through this particular link, if you can take the screenshot. These competitions, if you go through, this is also reported in this paper. So you can directly go to the paper also. It's not our paper, published from other people. And I mean, there are all the databases you can use for your research. And there are few open databases. It's not specific to one modality. It's cancer data, brain data, all data are there, MRI data is there. And the data volume is large. So I thought I should share these things because maybe the data, the link will give you a better idea that these are the things which you can work. So 15,000 patient is a big number. 14,355 patients. These are all big numbers. So these are good data set, public data set, available data set in which you can work in different modalities. Now the question is, in medical imaging or once you deploy machine learning, people used to say, I got 99% accuracy. So COVID, somehow CT, people already reported 99%, 99.95%. And life is different. The question comes into the picture, why should I trust you? And that is the answer needs to be given. Because the approach is, whatever the result you are getting, I am okay with that. But you have to give the explanation, the performance and the explainability. If you don't have explainability, whatever the performance you are getting, I am not interested in that. That is called the explainable AI, which is our new trend. Most of the European countries, Australia, they are started talking about EXI, explainable XI. So what is that? It is something like, suppose if you have a training data set, you have a learning process, and from there you are actually saying, traditional AI framework is saying, this guy is happy. Say confidence level is 0.95 and you are predicting he is happy. Why this model predicted that this guy is happy? Why not some other expression? Why did the model take this decision? Based on what? Which feature focused on? When it will fail? How can I correct the error? Why should I trust? Why should I trust that it is a happy face? So that AI model needs explainability. So explainable AI actually gives you that explainability model, from where you try to extract those inherent features. Like for example, the face, the wrinkles of around, the eyes, lips, maybe the cheekbones, etc. You try to find out, you try to think that which particular feature, how much it is actually involving in the entire process, how much it is contributing. And end of that, the explainable AI model will give you a trustable model, which actually these things will be clear to you. I can trust the model. I know the feature learning mechanism. It's not a black box to me. I understand the decision-making procedure. I understand why face is classified as happy. I know why this model failed. From where this model will fail, I understand how to fix the error. These things will be clear for explainable AI. So what I'm talking about you have a training data, you have a new machine learning framework, which actually gives you an explainable model and an explanation framework interfaces, by which the psychology of explanation will come out. The user can say, I understand why you are getting 99.9. I understand why you are not getting 100%. I understand why you succeed. I understand why you fail to get 100%. I know, or I trust you, and I know why you are getting error. So this explainability of the model needs to be there. There is a interpretable machine learning model which is called LIME. So it's a local interpretable, say, model of agnostic explanations. So suppose the machine learning is saying this is a Labrador, and I'm happy. 99% accurately it is saying it's a Labrador. Why? Why it is Labrador? So ask the question to the machine learning module. The module will tell you, the LIME will tell you, because this is the reason the machine learning is saying that it is a Labrador. The strong association with the predicted result. It's a kind of, say, the result is coming from, say, preterm, say, inception of the V3. Now that module will tell you that these are the features are there, and that much there, it is trustable, so you can trust. So Lime will categorize those things. The explainability of the model will be given by Lime, so that you can trust on the obtained result that this is a laboratory. So Lime actually helps to increase the confidence in machine learning model by understanding why they're returning certain prediction. So you can predict anything, but you have to tell why you are getting this result. That why should you need to explain. That is the explainability AI. So this is one emerging area where many people have started working. So you can also go through some of our recent paper in IEEE transactions where we work on Alzheimer, say on Lyme, etc. So you can search on that, goes through that. The last slide. See, if you are knowable and if you knows, it is trainable. If you are knowable, if it is unknown, it is generalization. If it is unknownable and it is known, certain cases the system actually not be able to train. That is universality. Deep learning can never learn those things. But the most challenging part is the last one. Unknowable unknowns. Think that paradigm. The unknowns and unknowable, that is the great firewall of knowledge. So that is called the total ignorance. It's a metaphysical statement. So we have to somehow break that great firewall of knowledge. So we will search for unknownable unknowns. Thank you. So I think now we have some time for question answer. If you have any question, if I able to solve.
Yes, participants.
Yes,
Kindly
participants.
ask the questions.
Yeah. Okay.
It's open for participants now. You can ask questions.
So I was audible?
Yes, sir, very well.
Okay.
And a very, very informative
Because
lecture.
this is
sir.
one is the biggest question, that am I audible?
Sir, actually, I have one doubt.
Yeah.
Sir, how can we relate deep learning with optimization?
How can I relate?
Yes, sir. Just suppose if we want to make some hybrid model, so how can we create that type of hybrid model using deep learning and optimization?
No, in cases of, see, if you talk about optimization, if you talk about heuristic or meta-heuristic algorithm,
Yes, I'm talking about.
either see, in different phases you can deploy. Like, say, for example, the data you are inserting, you're giving. So that can be a fused data. That can be based on the data which you actually use as a good data to train your system. So there can be a heuristic strategy which will select that these data will go, this data will not go. That is the first stage. Means I'm talking about the input. The input should be restricted. I should try to feed only good data, selected data, based on some selection criteria or some heuristic mechanism or meta-heuristic mechanism, which will decide that these things will go as an input, otherwise not. That is one. Second thing is, once we go for weight balancing, the weight balancing can itself an optimization problem. Means the balancing factor, if you somehow the variable, the variation is a tuner, so you are trying to balance those weight so that accordingly the activation function will work and it will pass to the intermediate layer. Then comes the overall model performance, like the number of hidden layer, the number, weight, the input, the output number. Based on that, there should be different level of parameter which you can train, which you can tune by some heuristic technique, so that the overall model complexity will be changed. So these are the some area, I think, where optimization can be deployed. But as I shown that ADAM is widely used. So ADAM is basically used for tuning those learning rates. Means by tune.
Means by using the meta-heuristic optimization algorithm, we can fine-tune the parameters. We can optimize the hyperparameters.
True.
So
But
can
the thing is, suppose if you are talking about some meta-heuristic algorithm, like say cuckoo search or bat, say Firefly or Zinc. The thing is, the problem is there is a biggest issue of convergence, because convergence issue, it takes lots of time. So if the data volume is large, the convergence will take a lot of time. So ultimately what will happen in medical science, we always try to go for faster result. So once we go for faster result, selection of these optimization strategies also very plays an important role. Means which particular optimization technique you will go for, meta-heuristic algorithm you will go for, because there are thousands of meta-heuristic algorithms. So all, I mean, you need to check so that the patient will not go to die. So this is one thing. And another thing is meta-heuristic is it's a kind of stochastic framework. So suppose you are going for medical image segmentation. So each and every image segmentation, that will give you different result if you not set the seed point, because for every cases you will get different segmentation result. So if you not get a generic image segmentation outcome for a particular modality for a particular patient, it's sometimes very vulnerable. It's not good. But still people used to work on meta-heuristic and publish lots of work on image segmentation on this. We also do the same, but did the same rather. But there is some problem. Yes, ma'am, please.
Any further doubts from participant side?
Sir, good evening, sir. I am Dr. Geeta, Professor, Computer Science Department, KLE IT, Hubbadi, Karnataka, sir.
Okay.
Very happy to listen to your session, sir.
Thank you.
Sir, I was working with one particular problem definition, that is impact of heart on liver and vice versa.
Okay.
So
you are trying to find out any correlation in between the heart disease and the liver. Okay.
Yes, sir. Yes, sir.
Cirrhosis.
And what I found was, like, independently I'll get the records, but when we take the related information of a particular patient, we are unable to find. So as it is more.
Do you have the same patient result?
Yes, sir. That question only I want to ask. Only few samples we got, sir. Having
very
same patient information, because they have not maintained it. Most of the hospitals, they have not maintained.
I understand.
Because it is time consuming process.
True. Long year back, ma'am, long year, I mean, say 19 years back, we also tried to correlate in between the stroke assessment of coronary and carotid calcification. But that time the challenge was the number of patients. So if you have number of patient pool like this to this, say 50 patient or 100 patient, if the pool is very less, I suggest you go for initially transfer learning. Transfer learning might give you a good result, because with these particular number of data, 50 or 100 or 150 data, you can't come up with a rationalized decision. Ultimately, whatever the correlation you will get, if you increase the data size, you will see it will be a failure case, maybe, mostly. So augmentation will not work fine, ma'am, because heart disease, there are many other things related. So liver also. So that means if you go for augmentation, augmented data is always synthetic data. So if you have ground data.
Yes, sir. Simulation, like we can go for simulated data, generated data.
Simulated data always you can go for, but as I said, the synthetic data is always synthetic data. It's not real data. So if the disease are vulnerable, you should try to come up with some sort of technique like a framework, frozen layer kind of the transfer learning module, VGG kind of module. That might be effective.
But collecting the data, even it is time consuming sense, but is it not the way of working with the things?
There is no way. There is no way. The major problem is we have data, we don't share. We share data, but we not reshare.
Yes,
so that is the major issue, ma'am. I mean, we collected data of multiple hospitals from Chennai, and there are lots of technical issues, like you have to go for signing, you have to go for contract with the hospital, putting their doctors in the as an author, co-author. There's lots of things are there. So I suggest you, ma'am, with a very small size data set, you should go for transfer learning kind of module. That might give you some result. You will try to increase the volume by some transfer learning. Then after that, you try to find out the correlation. Whatever the correlation is, if you find very less correlation, that also you can report. That there is a less correlation in between the heart disease and the liver disease. Okay, ma'am. So anything if you need, if you want to ask offline, you can mail me, or I am in LinkedIn also. So less, but not that much active in LinkedIn like Facebook, but I am there. So I will try to.
Yeah, and one more thing, sir. One more doubt.
Yeah.
Like now, when we have some idea, we want to publish. Like most of the reputed journals, they'll take more time to review and all. And if it get published in some like initial journals of the things wherein idea is good, and how these two can be compared, sir?
I'm not getting
and
your question.
which is better way of publishing, because some of the journals, they are taking more time to review. Review process is time consuming. But if
see, if you are coming with a framework, you should go for first copywriting. Copywriting will take 500, 17, 18 rupees, 50 rupees, and it will take 2 to 3 months time. So you can get an initial approval by copywriting. So your framework can be copyrighted. Second thing is, once you try to put the paper and parallelly people are working in this area, and these things happen. I mean, this is not in your control. So you can check in every Elsevier Springer journal, there is an option that what is the, say, turnaround time of the entire review. So you can check the on an average time how much, but in general 7 to 8 months is very common. So you have to keep presence, man. No other way. I mean, 7 months and 8 months you have to wait. So better is you should first copyright the thing, the framework, whatever you created. So that later you can claim. Okay, ma'am. Thank you.
Thank you.
Yes, thank you so much, sir, for most informative lectures from your side, sir. And the student definitely benefited from your lecture.
Thank you, ma'am.
If any query still now, you can ask to sir.
Yeah, sure, ma'am. Let me write my mail ID so that if anyone having any query, you can write.
Just go through in World Wide Web, find the sir having n number of papers and.
Oh, ma'am, those papers are it's nothing. It's a. I mean, if you, the thing is, the important thing is in the slide there are lots of links mentioned. There most of that materials I have taken from web, and few of the materials there are some copyright issues. So sharing the PDF will little bit of sometimes problematic. So that's why I always cited those. So if anybody wants for this in a particular mail, I will send to Madam. Madam, those links so that you can go through those links and you can explore more on this. Okay. So, thank you.
Thank you.
So, if you have any query, you can write through mail, or that other medias are also there. Okay, ma'am.
Thank you, sir. Thank you so much.
Thank you, ma'am.
Thank you, sir. Participants, thank you for today, and do fill the feedback form. Tomorrow you will be having your MCQ questions test also. So tomorrow we will meet again at 10:30. Anything else to announce?
So, ma'am, the MCQ, this feedback link you are going to share here, or you are going to send in the WhatsApp group?
Sir, that will be sharing here only. Okay, thank you.
Yes, all of you, please wait for the 5 minutes. Tomorrow is your session. We have scheduled your test at 3 p.m. और भी कुछ confusions है, and we will send your attendance soon, because last 4 days sessions we got that most of the participants have not joined properly. So this 75% is attendance and 60% is marks in a test is compulsory for getting the certificates. That's the important one, because we are not generating the certificate. The certificate itself generated through the ATAL website. So once we put your attendance in ATAL, it will automatically generate. So if your attendance is less, so we are extremely sorry, we will not provide the certificates to you all. So tomorrow test is compulsory. It is a 30 marks test. We already discussed in the previous session. But still, if you have any queries, you can ask. And our validatory session will start at 4:15. And you all should compulsorily attend this validatory session. It is only the 10 to 15-minute session for you. And we will take a oral feedback. So I'm requesting some of the participants from your side, you just give their name in a chat box, no problem. We will announce your name and you will give the feedback in that time. So if anyone interested, you just type in a chat box. I will send this your name to the our anchor for tomorrow feedback. We call you and you send your feedback.
Excuse me, madam. How many questions in the MCQ test, ma'am?
Sir, 30 questions will be there.
Okay. So can you provide some presentations regarding this ATAL web FDP?
Sir, we told earlier because the speakers will not provide the presentations to us. So we have a recording and we sent already. So you just check your email. All the session-wise recording we have sent. We already sent.
Yeah, yeah. Okay, okay.
And tomorrow session recording. Tomorrow you have your lecture related to the health, related to the meditations. So compulsorily you all attend this session.
Yes,
And
yes.
first session will taken by the IIT professor, Dr. Pachori sir. Okay, he will take this lecture tomorrow.
Okay, ma'am. Okay.
Yeah, if still any queries, because tomorrow directly you will go for the test, and also if you have any confusions, I'm here to clear your any points regarding your certificate getting and the test. So please ask.
Madam,
Ma'am, I
record
haven't got any mail
Yeah,
mail
ma'am.
we have
related to
not
video.
received, madam.
Just now I've checked. So can you please send in WhatsApp group so that